Hi, can you hear me? Yes, all right. So at this conference, it's like an optical interference coating conference. And most of the time, we're talking about coatings across large areas, which are many wavelengths wide, where you use the transfer matrix methods for simulation. But when you have, let's call it tiny thin film filters, when you pattern them, like on this picture, you cannot really use the transfer matrix method anymore because you're violating its assumptions. Now, why do you want these kind of patterned filters? Because, for example, you want to do multispectral imaging, where on each pixel of an image sensor, we put a different Fabry-Perot filter, dielectric Fabry-Perot filter, which sees a different wavelength. And that's how you make an image sensor that does both spectroscopy and imaging. Now, you, of course, trade off some spatial resolution. So because we pattern more filters, so an idea would be like, well, let's make smaller pixels so we gain that spatial resolution again. And then the natural question comes, well, what limits the miniaturization of these kind of filters? And I will highlight at least three of the effects. One is diffraction, the amount of reflections that can occur in the filters, and crosstalk, which is something newly identified in this case. Now, if you would simulate a Fabry-Perot filter with the transfer matrix method, typically you expect like a nice Laurentian curve like here on the left. But if you would measure the actual device or simulate it with a numerical method, you would get like this kind of collapsed curve, at least at oblique incidence. And there are two main reasons for this. One is diffraction, because we're getting basically small apertures on top of the filters, which increases the diffraction angle. So we basically have an averaging out of many filters, just like a focus beam. The second reason, which actually becomes important before diffraction and is the main cause of this curve, is that, well, we have now a finite filter. And at oblique incidence, there's only a small number of typically bounces before you reach the edge. So you can never reach a high quality resonance anymore because you can't have many bounces in your filter. And that's what makes this curve collapse quite quickly. And so if you want to, you can modify slightly the transfer matrix function. And I've used like the frequency domain approach, which we'll hear about more tomorrow. And that was very useful. And I've implemented this in a MATLAB toolbox if you want to use this yourself. Now, I also want to talk about a newly identified kind of limitation for these patterned filters, which is a specific form of crosstalk, which is kind of unique to patterned thin film filters. It doesn't happen with any other color filters in image sensors. And what happens is that light can somehow enter the wrong pixel. So what happens in this case is we have one filter here on the left, and light enters the Fabry-Perot filter, which now acts as a waveguide. And it propagates the light towards the neighboring filter, where it can couple to that neighboring filter, which is also a waveguide. And there it can continue to propagate and enter the wrong pixel, and maybe even 2 pixels further, and produce this kind of crosstalk bumps, which reduces your spectral and even spatial resolution. So that's confirmed also in numerical simulation. Now that all sounds like bad news. Some fundamental limitations of patterned filter scaling, the amount of reflections, diffraction, and crosstalk. But and actually there's a long way to go. So currently the commercial technologies, they're about, at last I checked, at around 5.5 micron pixels. And well, the image sensor world can already make 0.8 micron pixels, which is much smaller. And well, all these effects that I just mentioned, they get all worse the smaller you get. So that's kind of annoying. Now, I also want to bring some good news is that the crosstalk, this specific kind of crosstalk, can be greatly reduced in a very simple way, a cheap way, I would say, by exploiting one of the physical properties. And that is that it's highly asymmetric. So if you take two filters like this, the one on the left and the one on the right, if light enters from the left and goes to the right, there's crosstalk, but the amount of crosstalk from the right to the left is totally different. So it's almost zero, if you like. So there's an asymmetry, and that's something you can exploit. For example, you have an image sensor and you can freely pattern the filters on top of your sensor. You will pattern it in such a way that depending on the optics of your system, you minimize the amount of crosstalk that can occur by always patterning depending on the incidence angle. So in conclusion, like if you have thin film filters on large areas, which is the majority of the applications, use the thin film transfer matrix method. Works fine. If you use tiny thin film filters, be careful. Thank you.